Have you ever noticed how utterly unpredictable a single coin toss is, yet how strikingly predictable a million coin tosses can be? If you look at raw data, whether it's the heights of people, the temperature of a city, or the movement of the stock market, it looks like pure unfiltered chaos. But if you step back and look at it through the right lens, beautiful, elegant patterns begin to emerge. Statistics is the mathematical art of finding order in that chaos. It's how we measure the unknown and how we make confident decisions in a universe governed by uncertainty. To find these patterns, we first look at our population, the entire universe of things we care about, and extract a smaller, manageable subset called a sample. When we observe this sample, we classify its characteristics, which dictates exactly how we draw them. If the data is qualitative, like eye color or brands of cars, we can't do math on it. We just count categories. For this, we use bar graphs or pie charts to easily compare the sizes of groups. The numerical data is called quantitative. If it's discrete, meaning counted in whole numbers, like the number of your siblings, we visualize it with a stick graph. But if it's continuous, meaning it can be any decimal like time or weight, we group the data into classes and draw a histogram, where the area of each block represents the frequency of that data. Once we have our data, we want to summarize it. We start by finding the center. Imagine your data points scattered on a 2D plane. But these aren't just dots. Think of them as having different weights or sizes based on their value. The mean is like a shiny, glowing center of mass. If a massive outlier drops onto the plane, you can physically see its gravity pull that shiny mean toward it. The median, on the other hand, resists this pull, just looking for the middle dot, regardless of its weight. But knowing the center is only half the battle. We need to know the spread, the messiness. The ultimate tool for this is the standard deviation. Let's look at this beyond the usual perspectives. Let's go back to our dots on the plane. Imagine a glowing tether connecting every single dot to that shiny mean. The standard deviation is essentially the average length of all those tethers. If the standard deviation is small, the dots are tightly hugging the center. If it's large, they are scattered to the edges. Another way to visualize this is by plotting our data into a continuous curve. The standard deviation is quite literally the width of that curve, specifically the distance from the peak to the inflection points where the curve stops curving down and starts flattening out. But not all curves are perfectly symmetrical bells. If the data is heavily pushed to one side, leaving a long trailing tail on the other, we measure that with skewness. And for the thickness of those tails, or how sharp the peak is, we measure this with a parameter called curtices. High curtices means you have fat tails, meaning extreme outliers events are much more likely to happen than a normal distribution curve would predict. Up to this point, we've only looked at one dimension at a time, but the universe is interconnected. We can study as much variables as we want, but for the sake of simplicity, let's only track two variables, x and y. With that, we enter the 2D world of bivariate statistics. Imagine a cloud of dots scattered across a screen. How do we find the center here? If we completely ignore y and smash all the dots down onto the x-axis, the center of that new 1D line is the marginal mean of x. It's the overall average, blinding itself to the other variable. But what if we don't want to ignore y? What if we take a thin vertical slice of our data, locking x at one specific value, and only look at the dots inside that slice? The center of just that slice is the conditional mean. As we sweep across the x-axis, slice by slice, these conditional means trace out a path, showing us exactly how the center of y shifts as x changes. Now, what if the path doesn't dance at all? What if, no matter where you slice x, the conditional mean of y stays exactly the same? This leads us to independency of variables. If two variables are perfectly independent, it means a change in x doesn't affect y at all. Knowing x gives you zero information about y. But here where most people get confused. They assume independent is the exact same thing as uncorrelated. It's not. We use the linear correlation coefficient, or rho, to measure if x and y move together. If rho is 0, we say that they are uncorrelated, but rho has a blind spot. It only looks for straight lines. Imagine your data points form a perfect, symmetrical smiley face, or a perfect circle. Are they independent? Absolutely not. If I know your x coordinates is at the far edge of the circle, I know exactly where your y must be. They are highly dependent. But if you ask rho to draw a straight line to best fit through that circle, the line will just lay completely flat. Rho will equal 0. So remember this golden rule. True independence guarantees that variables are uncorrelated, but not necessarily vice versa. Being uncorrelated does not mean they are independent. They might just be hiding a beautiful nonlinear pattern. To truly capture these curved nonlinear patterns, we need something better than raw. We need to understand the anatomy of chaos through variance decomposition. Think of the total chaos, the total variance of y. We can mathematically split this chaos into two distinct patterns. First, the chaos inside each of our vertical slices, how scattered the dots are from their own conditional mean. This is the unexplained noise. Second, the variance of the conditional means themselves, how much the glowing path dances up and down. This is the variance explained by x. Total variance equals explained variance plus unexplained variance. By taking the explained variance and dividing it by the total variance, we get a powerful new parameter, the Pearson correlation ratio, or eta squared for short. While rho measures how well your data fits a straight line, eta measures how well your data fits the curve of the conditional means. Because of this, rho squared can never be greater than eta squared. It's mathematically impossible. Eta is the ceiling. And in that rare, beautiful case where rho squared perfectly equals eta squared, it means the curve of your conditional means is, in fact, a perfectly straight line. So, from finding the center of mass to measuring the tethers of standard deviation to slicing through 2D space to watch variables dance, that is the elegant machinery of statistics. It's the geometry of finding truth in the noise. I hope you understand the beauty of this science. Thank you for watching.